right, welcome to Chapter 7, Measurement and Assessment. For this unit, we're going to go over some general issues about measurement, different kinds of variables. We'll talk about validity and reliability in terms of research. So in Chapter 2, we talked about categorical and continuous data as two sort of classifications of data that we will often encounter. These are the most important classifications because in many respects, the kind of data you have influence the kind of statistical analyses that you perform. I liken statistical analyses to tools in a toolbox. So if you imagine a Phillips head screw, if you have a Phillips head screw, you know you need a Phillips head screwdriver. On the other hand, if you have a flathead screw, you need a flathead screwdriver. Statistics are like those screwdrivers, and the data you have are like those screws. So if you know what combination of categorical and continuous data you have, then it makes it easy to know which statistical tool you would use to address that question. So for example, if you have a categorical independent variable like gender, for example, males and females, and you're looking at differences in reaction time, which would be a continuous variable, and that would be a continuous dependent variable, then the tool that you would reach for would be an independent sample t-test. If we're looking at the relationship between reaction time and a person's level of income, those are both continuous variables, and we're talking about relationships, then we look at a correlation. The point here is that categorical and continuous are very important to understand because they help to determine what kind of statistical analyses you're able to use. Now, there are other there are further classifications that we can get into, so we can break these up a little bit further into these various scales of measurement. Nominal, ordinal, interval, and ratio. Now, nominal is categorical data, and these are non-quantitative data. So these are any variables that do fall into discrete categories but don't have numbers that are associated with them that are particularly meaningful. So we can think of things like the country you're born in, college major, personality type, gender, ethnicity, religion, these kinds of things. Now, when we do our data analysis, we will use numeric codes for our categorical variables. So for example, we might code males equal to 0, females equal to 1. This is useful because when we're entering data, it's a lot faster and more efficient to just type 0 for male and 1 for female. But those numbers themselves are completely meaningless, and that's what makes this nominal data. 1 for female does not mean that females are 1 more than males, right? We could have used any random numbers. Now, an ordinal scale is similar to nominal, so we've got categories, and we're associating numeric values to these categories, but for an ordinal scale, these numeric values actually have some meaning. So you can think about this as being sort of a rank order. If you think about the categories of like times of day, you might have morning, afternoon, and night. And those are categories, and you could associate numbers to them. Morning would be 1, afternoon would be 2, night would be, or evening would be 3, and those numbers actually do have some level of meaning to them. Okay, so you can think of rank in class, these kinds of things. So they're categorical, but these values have meaning, and they typically indicate rank order. However, the numbers themselves are arbitrary. Right, so I could have made morning 25, afternoon 50, and evening 75. Right, the numbers we use themselves aren't really meaningful, but they do have meaning in terms of rank order. You can think about the pain assessment scale from the hospital or the doctor's office. So you come in and they say, on a scale of 0 to 10, or using these faces, how much pain are you feeling right now? Now, for me, maybe I have a very high tolerance to pain and I have a nasty laceration on my hand. I might put that at a 4, but for someone else with that same injury, they might put that level of pain at an 8. And And additionally, the distance between a 1 and a 2 on the pain scale for me might not be the same as the distance between a 5 and a 6 on the pain scale for me. So one of the key things about these ordinal judgments is that they rank order these categories, but there's not necessarily the same distance between one level of the category and the other. So in terms of the pain scale, the difference between 2 and 3 for me might not be the same as the difference between 8 and 9, for example. Now, for an interval scale, now we're getting into the land of continuous data. So nominal and ordinal, typically categorical data. Interval and ratio are typically continuous data. For an interval scale, now the distance between the points on this scale is the same. So you can think about, again, we're ordering things, we're giving it numeric values. The distance between these things is the same. But there's no zero that's meaningful, and that's the difference between interval and ratio. For interval, there's no real meaningful 0 point. So you can think about temperature as being an interval scale. There is technically 0 for temperature if we talk about Kelvin. But for all intents and purposes, temperature is a continuous data point. And the interval between degrees of temperature, so the difference between 5 and 10 degrees Fahrenheit, is the same as the difference between 85 and 90 degrees Fahrenheit. Now our experience is different, but the distance on the scale is the same. You can think about time of day as another version of this interval scale when we have a 12-hour clock. So the amount of time, the distance between 1 p.m. and 2 p.m. is the same as the distance between 11 and 12. And this is what makes this an interval scale. Now, when you add in a 0, true 0 that has meaning, then you have ratio level data. So this allows for ratio type comparisons, so twice as high, half as much, these kinds of things. So the 24-hour clock, if we start at 0 and go to 24, right, this has equal intervals and it has this true 0 point. You could also think of response time, so you could not respond at all, up to however many seconds, points in the class. So theoretically, someone who forgot to drop the class could end up with 0 points in the class. There's a meaningful 0, and the distance between 1 point and 2 points is equal as the distance between 5 and 6 points. And because of this, we can do these ratios. So 280 points is twice as much as someone who earns 140 points. That's what makes this ratio level data. So these are the 4 different subcategories of data, but again, continuous and categorical are really the critical ones. Now, anytime we're looking up research, anytime we are conducting research, we do need to be concerned with the validity of our measures. Validity equates to accuracy. So how accurately does my measure the thing that it is supposed to measure? How accurate is my interpretation or the consequences of these test measures? So for example, let's say you designed a measure of depression. The question of validity is how well does your depression measure that you created actually measure depression and not other things that are unrelated to depression like anxiety? Or the ACT purportedly measures college readiness. So how well does the ACT tap into this construct of college readiness compared to other similar constructs like your level of studying or your education that you receive? Now, anytime we measure a construct, anytime we're setting out to measure anything, we will capture data that will involve both the true score and the error. So we take for a moment this assumption that there is a true level of depression, or there is a true level of your college readiness. When we measure your depression with a scale, some of what we measure will contain this true score, this actual thing, and some of what we measure will contain error. Now, the observed score is this data that we're going to gather, right? So the actual data that we have, the survey responses, whatever it is, these are our observed scores. your actual score on the ACT. True scores are these actual unknown values that correspond to this construct of interest, right? So, this is your actual objective level of depression or your actual objective level of college readiness. Now, the thing to know about the true score, part of the reason why I have this in quotes here, is because typically we can't really ever know this true score, right? We're trying to measure this thing and we know that this thing exists. We assume that this thing exists. But because every time we do a measurement, it's going to contain some error, right? Our measurements are going to include only part of this true score, to some degree of this true score. Now, there are two different kinds of error that will show up in our measurement. So if you imagine that we have this observed score, your actual ACT score, or your actual depression score, some of that score is going to be your true level of depression or your true level of college readiness. But some of that variability in that score is going to be error. It's going to be variation in how well you performed or how you responded. That is due to sources that are other than depression and other than college readiness. And there are two kinds of error that we deal with, and these kinds of error actually map onto the other kinds of variables we talked about when we talked about experimentation. So random error, non-systematic variation in the observed scores, and we can sort of equate this to these extraneous variables. These are things that are going to influence how you score on that dependent variable, but that are completely unrelated to the variable of interest, and they're random, right? They don't affect anybody systematically. So, your depression or your ACT score might be influenced by when you last ate or how much sleep you got the night before. But this is going to be random for our participants, right? Some person's going to sleep more, some person's going to sleep less. It's kind of random. There are also systematic errors, and you can equate these to sort of confounds, right? These are variables that systematically vary with the independent variable or with the measurement across the sample, right? So this is error that's going to influence everybody's observed score across our sample. So you might think for the ACT, the quality of K through 12 education, or the amount of SAT prep or ACT prep courses that you were able to take. These are going to systematically influence ACT scores across measurement. So when we end up with our observed score, it's always going to contain these three things: the true score, the actual variable we're trying to measure, systematic error, and random error. Now, with random error, we can sort of redistribute the random error throughout our conditions. For example, if we're doing an experiment using random assignment. When we decrease systematic error, so if we can have a tightly controlled experiment and we make sure that our conditions are as equal as possible, right, decreasing systematic error is going to make our measurement more accurate. If we increase systematic error, that means that our observed score contains less of this true thing we're trying to measure, less depression, less college readiness, and more these other things that are systematically influencing measurement, then we're going to have a less accurate measure. It's going to be less valid. So when we talk about validity, one form of validity that we're interested in is what we call construct validity. And this is kind of what we've been talking about all along. Do the measures actually assess the constructs that they are designed to measure? Right? If I have a measure of college readiness, does it measure college readiness and not, for example, whether or not you are part of the dominant culture or whether or not you went to a school that had more financial resources? Right? So do the measures actually assess what they're trying to measure and nothing else? Ideally, what we want to do is reduce both systematic and random error to the degree that we can, so that we can get more of that true score in our observed score. Now, how do we know whether our measures are valid? There's a few different forms of construct validity that we can talk about. So face validity, and you can think about construct validity as sort of the overarching heading here, and then the rest of these validities sort of fit as subpoints within construct validity. So face validity is subjective evaluation of the measure. You can think about this as sort of experts taking a look and saying, like, yeah, this sounds like it measures intelligence. And these questions look like they measure depression. It's sort of the weakest form of validity, but it's just this idea of like, hey, when I read these, they sound to me and they sound to experts like questions that will measure this construct that we're interested in. Now, criterion validity is a measure of performance. So how well does our measure predict related variables, right? So if the SAT and the ACT both both are designed to predict college readiness, then they should probably have a strong influence. They should predict how well people are going to do in college, right? Their freshman year GPA, for example. Okay. So if I know your score on the ACT, then that should tell me something. I should be able to predict how well you're going to do in college. Now, convergent validity is relationships between your measure and independent measures of the same construct. So this is convergent, things coming together. So if the ACT is supposed to measure college readiness, then the ACT should be strongly related to other measures of college readiness. So again, if the ACT and the SAT measure college readiness, and we have you take both of them, you should score high on both of them, or you should score about the same on both of them. And in our sample, there should be a strong relationship, a correlation that shows that these two variables are strongly related to each other. Divergent validity is a sort of opposite. So this is showing that your measure does not measure these other things, right? Similar but unrelated distinct constructs. So if you are doing a study of intelligence, it shouldn't be really related to memory, right? It shouldn't be related to memory at all. Or if you're doing a study and you have a measure of depression, it shouldn't be related to anxiety. If you have a measure of college readiness, it should not be related to level of income or socioeconomic status. But it turns out that these things tend to be. So divergent validity is showing that your measure is valid by showing that it does not relate to these unrelated constructs. Now, when we're talking about validity, we're talking about accuracy. How accurately do we assess or tap into the construct of interest? Reliability on you can think about this, as sort of hitting the bullseye on the target. If the bullseye is that true score, then hitting that bullseye is accuracy. Reliability, on the other hand, is consistency. So if validity is accuracy, then reliability is consistency. So validity is sort of hitting the bullseye. Reliability would be hitting the bullseye every single time, right? How well does my study measure consistently? Or how well does my measure consistently? I use the word measure a lot in this lecture. So is my measure reliable? Now, there's a couple different kinds of reliability that we can talk about. So test-retest reliability is about consistency over time. So if I give you a test that's designed to measure intelligence, or if I give you a version of the ACT, and then 3 months later I have you take the same or similar version of the test, and you haven't studied or done anything different in those 3 months, if those tests are reliable, then presumably your scores should be nearly the same. Right? If you take the ACT in March and then you take it again in June and you haven't studied or done anything differently, and it purportedly measures college readiness, which is a stable construct, then theoretically your score should be about the same. Okay? Consistency over time. Now, when we actually do this, by the way, a lot of times we will use equivalent forms, right? So one question you might ask is, well, like, of course your score is going to be the same. It might actually even be higher. Like if you take the same test twice, you're going to get better at it the second time around. And this is true. Oftentimes what we do is we use what's called equivalent forms tests. So if there's 100 questions in this intelligence test and we want to demonstrate test-retest reliability, we will get a random set of 50 and then give you a random set of the other 50 at time 2. And we'll do that for everybody so that you're not getting the same exact questions. They're all part of this one measure. Now, internal consistency is another form of reliability, which is about the degree to which all of the items, all of the questions are all consistent. Are they consistently tapping into the same idea? Or in other words, not to confuse that with validity, but are participants responding in the similar fashion to similar questions? Um, so if I have two questions, on a scale of 1 to 10, how much do you like the color blue? On a scale of 1 to 10, indicate whether the color blue is your favorite color, right? If that measure is reliable, if I say I like the color blue on question 1, I should say I like the color blue on question 2, right? People are responding in a similar fashion. Okay. If you've ever participated in research, you may have noticed that some of the survey type questions, some of the measures will have the same question worded 15 different ways. And part of this is we're trying to assess different facets of these constructs. So for example, when we're talking about emotional empathy, how empathetic did you feel towards another person? A lot of the words that we'll use are words like kind and soft-hearted and concerned. How concerned did you feel for this person? How kind did you feel towards this person? How soft-hearted did you feel towards this person? All of those questions are designed to tap into this idea of empathy, and you should be responding consistently. If you have high empathy for this person, you should be scoring highly on these questions, 777. If you hate this person and you don't have any empathy for them, then you should be scoring low. But what you shouldn't be doing is saying, I love this person, I feel kind towards them, but not soft-hearted at all. But definitely concerned for them, right? That would be inconsistent responding. That would decrease this internal consistency. Now, split half reliability is when we determine internal consistency by comparing the first half of the items to the second half of the items. And you can think about this as a correlation, pretty much. So how well does the first half of the items correlate with your scores of the second half of the items? Now, this is sort of an outdated way of thinking. Now, what we typically use, and something that you will commonly see, is what we call Cronbach's alpha. If you ever reading through a method section and you see a statement of something like, our measure had adequate internal consistency, alpha equals, this is Cronbach's alpha that we're talking about. And Cronbach's alpha is the average of all possible split half reliabilities. So if you imagine we've got a 6-item measure, we could do a split half comparing items 1 through 3 and 4 through 6. And then we could do another split half where we compare items 2 through 4 with items 5, 6, and 1. And we could break this up into all possibles. And Cronbach's alpha is the average of all of these possible split half reliabilities. It's given the symbol A, and it ranges from 0 to 1. So 0 is you're asking wildly different questions. How much do you like the color blue? How good are you at repairing electronics? Right, completely random questions. 1 means you literally ask the same exact question 10 times in a row, and all the participants responded in exactly the same way 10 times. So if the first person put 7, they put 7, 7, 7, 7, and the next person put 6, they put 6, 6, 6, 6 for all of them, right? So this is the range of Cronbach's alpha. 0 to 1.0. Generally speaking, and it varies from discipline to discipline, but anything higher than 0.65, I believe your book says 0.7, is deemed as acceptable reliability, which means that there is some variability in how people are answering the questions, but generally speaking, if someone is scoring high on the measure, they're scoring high on all of the questions. If someone's scoring low on the measure, they're scoring relatively low on all of the questions with some variability in between. And this indicates good internal consistency, that people are responding to the measure in a similar fashion. And when I say similar fashion, I mean consistent with their other responses. Again, so if you score high on question one, you're scoring high on question two and three as well. You're not sort of bouncing all over the board. Now, there's other forms of reliability, so we can talk about inter-rater reliability or inter-observer reliability. This is when we're doing observational data, and we want to demonstrate that the observers are recording their observations in the same way. So the idea behind observational data is if you've set up your procedures correctly, if you've clearly defined exactly how you're going to make your observations, and you have two observers who have been trained in how to make these observations, and you show them both the same scene, they should record that scene in the same way. So for example, I'm currently doing a study where I'm looking at parking lot behavior. And we are recording the amount of time it takes people to pull out of a parking spot. Now, I've clearly defined to my research assistants exactly when we're going to start the time and when we're going to stop the time, what we're going to count as pulling out of a parking spot. For example, only people backing out, not pulling out forward. Um, and the idea is that if I have clearly defined how my observations are going to be made, then if I take two people, two research assistants, and I have them observe the same car backing out, they should both record the time almost identically or pretty darn close. And this tends to happen when you have clearly defined set of procedures for making your observations. And we want this because we want to make sure that people aren't misjudging or misinterpreting. So, for example, if you are studying aggressive behavior at a schoolyard playground, and two kids are chasing each other, and one kind of puts his hand on the back of the other and pushes him, does that count as an aggressive behavior, right? Are they playing tag or are they being aggressive towards one another? So you need to have clearly defined set of rules and structures in place so that your observations can be made objectively and consistently. Now, we typically, there's two ways that we can assess inter-rater reliability. So if we're talking about categorical data, then we're asking the question about the degree to which two or more observers agree, the percentage of agreement. So if I'm having people look at photographs and I want them to identify whether the person is male or female, we would mark it as a 1 if they agree and a 0 as if they disagree. And then we would calculate the percentage of agreement. Out of 200 photos, how many of them did they agree on, right? And if we had good inter-observer reliability, we would expect a high percentage, 95% agreement, 98% agreement, something like that. For continuous data, we're looking at the correlation between the ratings. So if you think about my parking lot data, if I have two observers look at the same scene and they record the amount of time it takes someone to pull out of the parking lot, and we have many, many, many of these observations, we should be able to throw that in and get a correlation that's really close to 1.0. If everyone's using the same rules to make their observations, then the two observers should observe the scene similarly, and our data should be highly correlated between these two observers. Now, putting this all together, one thing that is key to know is that just because you have reliable measurement doesn't mean it's valid. Reliability does not equal validity. You can be reliably inaccurate. So, for example, I can get on a scale, and when I get on the scale, it tells me that I weigh 100 pounds. And I step off the scale and I get back on 5 minutes later and it says 100 pounds. And I get back off the scale and I get back on another 5 minutes later, it still says 100 pounds. That is a very reliable scale. It's giving me the same reading every single time I'm using it. But I do not weigh 100 pounds. I'm more in the neighborhood of 200 pounds, right? So it's not an accurate measure. It's not valid. So something can be reliable, but not valid. Ideally, we want measures that are both reliable and valid. One piece of advice that I often give to students when it comes time to develop a dissertation or a thesis proposal is to don't reinvent the wheel, right? If you need to measure self-esteem, for example, there is the Rosenberg self-esteem scale that already exists and already has been demonstrated in previous research to be both reliable and valid, right? So anytime you're looking for measures, you want to use the existing literature to find reliable and valid measures. Now, if we put this in terms of the bullseye metaphor that we went with before, here we've got a bullseye, so the target, the center of the target is that true score that we're trying to measure. Um, Here we've got a reliable but not valid measure. This is like the scale that tells me I'm 100 pounds. We're getting a consistent grouping of darts. So imagine these little blue dots are darts. We're hitting the target consistently in the same place, but we're off, right? We're not measuring the construct. We're measuring something way over here. This is a valid measure, but it's not really reliable. So, sometimes it hits the true score, sometimes it doesn't. We've got an equal spread over the whole target, but it's just kind of all over the place. Like sometimes it works, sometimes it doesn't. So it's valid, but it's not really reliable. It's not consistently measuring. This is neither valid nor reliable, right? So again, if the true score is this sort of red dot in the middle, we want to capture all the different facets of this construct. If we are not reliably measuring and we're missing half of the target, then we're not valid at all. And then for valid measure, we've got all of our darts hitting the center of the target and we're doing it consistently, making it both reliable and valid. So that's it for measurement. As always, email me if you have any questions.